So in the last video, we analyzed the acceleration of a particle that is moving with simple harmonic motion. And in this video, we can analyze the velocity of a particle in simple harmonic motion. So what is the velocity like? Because we need to know these entities to describe the motion completely. So we know what the acceleration is. Now let's consider what v is. Now this is the characteristic equation of a motion, of a simple harmonic motion. Then I'm going to rewrite like this. This is called a differential equation. This is actually called the second order differential equation. And you don't know how to solve these types of differential equation. This is out of your scope. So to solve this differential equation by integration, what we do is we make a simple substitution here. We're going to change this uh, second order derivative of x with respect to time with velocity. So we're gonna use a simple tool. It's called using chain rule. We're gonna do this. So let's start with this one. So what is v? V is dx over dt. V is dx over dt. Okay. So it's not very clear. V equals dx over dt. Right. Now what I'm going to do here is that I'm going to differentiate this equation with respect to x, not time, with respect to x. So dv by dx would be, now you know that since dx by dt, that means x is a function of time, because this is a moving particle. So when a particle is moving, it will be a function of time. So that's why it is differentiable with respect to time. Now since we are differentiating this with respect to x, we're going to have to use chain rule. If you remember, then instead of deriving this with respect to t, with respect to x, I'm going to derive this with respect to x here. So dx by dt, I'm going to derive this with respect to x, this quantity. If I derive this with respect to x, I'm going to have to multiply this by dx. So since we cannot derive this with respect to x, we derive this with respect to time. So you can have to multiply this by dt over dx. dt over dx. So what is this? This is d squared x over dt squared. And dt over dx, we can write it as the reciprocal 1 over dx over dt. Dx over dt is v. We start with this equation dx over dt is v. So we can write this as dv over dx is equal to d squared x over dt squared. Right. So what we did here is that we replace this entity with a different derivative. Right. So let's replace this one now. I'm going to replace this one with v dv over dx equal minus omega square x. Right. Then I'm going to cross multiply this. Then I get v dv minus omega squared x dx. Now I can integrate both sides, because now on the left hand side we have only v terms. On the right hand side we have only x terms. So we can integrate them separately. So when v integrate with respect to v, you get v squared by 2, and here you get minus omega squared x squared by 2 plus an integrating constant. So we have to find this integration constant. So to find this integration constant, we're gonna look into the simple harmonic motion. So as I said earlier, when a particle is following a simple harmonic motion, what happens is that when it just passes O, it moves with deceleration until it becomes rest, then turns around and comes back. So until it becomes rest, when will it become rest? At the greatest displacement. So greatest displacement is called the amplitude. At the amplitude, the velocity of the particle is 0. right? So we're going to use this data to figure out C. So that means at x equal a, let me write it here. Right. At x equal a, the velocity is 0. This is the data we use. So we use this, velocity is 0, so this is 0 equals minus omega squared a squared plus c. This implies c is equal to omega squared a squared. Right. Now we can substitute this into the equation here. Then we can obtain, right. So this becomes now v squared by 2 minus omega squared x squared by 2. Alright, so there's a 2 here, I forgot it, plus omega squared a squared by 2. So 2 cancels off and we are left with v squared equals, we can factor out an omega squared. If I factor out an omega squared, this is a squared minus x squared. Right. So this is the equation that tells us the velocity of the particle at a particular displacement. Right. So let's write this somewhere. V squared equals omega squared a squared minus x squared. This equation tells us what the velocity is. Let me get rid of these. Right. So let's analyze this equation. So velocity becomes 0 at this point. That was the data we use. And if we graph this one, right. So this is v squared versus x. I'm going to graph v squared versus x, not v versus x. I'm going to graph v squared versus x. So if I graph this one, the origin means at x equals 0. So what happens at x equals 0, we get v squared equals omega squared a squared. Omega squared a squared, that is the maximum value. At the amplitude, x becomes a, so this part becomes 0. So at the amplitude, these parts become 0. So we can extend this minus a. Now, what is the shape of this equation? This sort of looks like y equals some constant c, another constant b minus x squared. So this is y equals minus c x squared plus cb, right? So this is actually a quadratic function. So quadratic function which is a maximum, therefore it would take the shape like this, right? This is the shape of the function. So what does it tell us? It tells us that the maximum velocity is obtained at the 0 point x equals 0, that means at the center. So we get the maximum velocity maximum, v max. So let me take the amplitude, the absolute value, max, absolute value of the velocity. At x equals 0, v squared equals omega squared a squared. So the absolute value would be omega a. Just have to take the square root. When you take the square root, you get plus or minus omega a. So I'm just going to take the absolute value, that is equal to omega a. The minimum velocity the absolute value would be 0. That is when the particle is at its highest displacement. Right. Thank you for watching.